Example 1.11. The distance between points P and Q in R2 is given by the Euclidean distance formula. Distance from P to Q equals square root of the sum of the squares of differences between corresponding components. Then, once we have the distance defined, we can say the set B of x epsilon is the set of all points P in the plane, such that the distance from x to P is less than epsilon. That's going to be called the open ball of radius epsilon centered at x. So that's illustrated right down here. The open ball of radius epsilon centered at x is the set of all points P whose distance from x is less than epsilon. Okay. If we take the collection B of all such open balls of radius epsilon centered at any x in the plane, that is a basis for a topology on R2 called the standard topology. So, another definition, 1.3, let X be a topological space and let X be an X. An open set U containing X is said to be a neighborhood of X. Not really any new ideas here, just a convenient new word to describe an open set containing a point. Alright, and now theorem 1.4. Let X be a topological space and let A be a subset of X. So you can look at the picture here. Then A is open in X if and only if for each point X in A there exists some neighborhood U of X which is contained in A. Okay. This X and U here is a little bit redundant because we've already said that U is a neighborhood of X. This theorem is called the local characterization of open sets because it says that in order for A to be open, it's enough to just look at one particular point in it, well, at every point in it, and make sure we can find a neighborhood of that point contained in A. Okay. So this is a convenient way often to show that a set is open. All right, so here's the exercise we are going to do using this stuff. 1.17. An open half plane is a subset of the plane in this form. Set of all points x, y in the plane, such that ax plus by is less than c. For some constants a, b, and c in the real numbers, with either a or b non-zero, prove that open half planes are open sets in the standard topology on R2. Okay, well, the line, well, ax plus by equals c is going to define a line in the plane. And then the set of all points where ax plus by is less than c is going to be all the points either on one side of this line or on the other side, right? Not including the line itself. So let's call that open half plane H, and I tried to shade in this side of the line to indicate H. Now, by theorem 1.4, in order to prove that H is open, all we have to do is take any element of it, for example PQ, and show that we can find a neighborhood of that point PQ which is contained entirely in H. Okay. Now combine that with the fact that for the standard topology on R2 we have this basis of open balls. It's enough to find some open ball containing PQ which is itself contained entirely inside this open half plane H. Okay. Because that open ball is certainly a neighborhood. It's an open set. Okay, so we need to find a delta to make this work. So to begin, let's assume that we have a point PQ in this open half plane H. And what that means is that PQ satisfies this inequality. So AP plus BQ is less than C. Okay. And what we need is to find some ball about PQ of radius delta. You'll see in a bit why I'm using delta instead of epsilon here. Such that this ball is a subset of the open half plane H. All right. Well, in other words, what does that mean? We need to find some delta greater than 0 such that any point x, y in this ball is contained in H, right? So how do we say that? Such that if the distance from PQ to some other point x, y is less than this delta, so that x, y is in that ball, then that implies that the point x, y is in H. Right? And x, y in H means that ax plus by is less than c. Okay. So that's what we need to do. Find the delta such that if xy is within delta of pq, then ax plus by is less than c. Okay, well, let's draw a picture for a moment, thinking about this inequality here. Actually, let me write down one more thing before we do that. I claim that it suffices to show that the distance on the real number line between AP plus BQ and AX plus BY is less than C minus AP plus BQ. Okay. Why is this? Well, now we can try to draw. So here's my number line. And, okay, I start out with some value AP plus BQ and some constant C. And what I know is that the distance from this AP plus BQ to AX plus BY is less than this distance, C minus AP plus BQ. In other words, AX plus BY must be contained in this open interval about AP plus BQ with that radius, right? So for example, maybe AX plus BY is right here. Okay. Now what I can conclude from that is precisely what I need, that AX plus BY is less than C. Okay. So what I'm saying is that we need to find a delta such that this inequality is true, and that will automatically imply what we want. So we just need to aim for this. Okay. Now this difference on the right-hand side here, that's just a constant, right? So let's just give that a name, epsilon. Okay. So we will let, as I just wrote up there, but let's make it official, epsilon equals C minus AP plus BQ. Okay. All right, well now let's do some computing. All right, so we're aiming for this, remember, so let's see how to get there. So AP plus BQ and AX plus BY. The distance between those two numbers, well, just rearranging some things and regrouping, we get that that's equal to the absolute value of A times P minus X plus B times Q minus Y. And by the triangle inequality, that's certainly less than or equal to absolute value of A times P minus X plus B times Q minus Y. Okay, and because the absolute value of a product is a product of absolute values, that's the same thing as absolute value A, absolute value P minus X plus absolute value B, absolute value Q minus Y. Good. Now, remember, we need this left side up here to be less than this constant epsilon, whatever epsilon is. And so to make that happen, we could force each of these summands here to be less than epsilon over 2. And we know that'll happen if we can ensure that absolute value p minus x is less than, well, 1 over absolute value of a times epsilon over 2. And moreover, that absolute value q minus y is less than 1 over absolute value b times epsilon over 2. Right? Then each of these products will be less than epsilon over 2. You add them up, it's less than epsilon. And we would be done. So still trying to find some delta which would make that happen. All right. Well, I claim that we can let delta be just the minimum of these two quantities. Okay, epsilon divided by 2 absolute value a, and epsilon divided by 2 absolute value b. Okay. So that's our delta. And then I claim that it suffices to have absolute value p minus x less than this delta, and absolute value q minus y less than this delta as well, because if they're both less than delta, they're less than the minimum of these two, then certainly absolute value p minus x is less than this one, and absolute value q minus y is less than this one. Okay. So we need to find, or we need to convince ourselves that these two inequalities hold. Okay. But that's not too bad. Note that assuming, as we are, that the distance from p to q, from pq to xy is less than delta, implies both of these inequalities. Okay. For example, let's look at absolute value p minus x. Right. That is equal to the square root of p minus x squared, right? And that's certainly less than or equal to square root of p minus x squared plus q minus y squared. Right, because to go from here to here, we're just adding something non-negative under the radical, and that's certainly not going to make it smaller. But that's just the distance in the plane from the point PQ to the point XY. Right. So if we assume that this distance in the plane is less than delta, then we get that the distance between the first components of these 2 points on the number line is also less than delta. Okay, and the same sort of argument would work to show that the distance between the second coordinates of these 2 points is less than delta. So we're good. We have indeed found a ball about the point PQ of some positive radius, which is a subset of this open half plane. So the open half plane is open in the standard topology on R.